G'day, this is Shane Hale from Emerson Gas Chromatographs, Rosemount Analytical. Welcome to our fourth of the fifth series of webcasts. We're about to start. This one's going to be monitoring of GC performance. Thank you very much for attending, and hopefully you find this informative. Like I said, this is the fourth in a series of 5 webcasts. The other webcasts are all available on the website. At the end of the presentation, we will show you the link and how to find those webcasts. And also, this webcast will also be recorded. As usual, we're still starting to see people join in just after the start. So what we'll do, we'll just wait 1 or 2 minutes. But before we do, what I will like to show is just put up a poll. Hang on, I'm having trouble with my interface here. Just for some reason it's not moving forward. Let me see why. There we go. So I'm just going to have a poll here to just see what level of experience we have with people on the call, and based on this I can kind of change a little bit of what I talk about as far as the information throughout the presentation. So if you could just answer this poll quickly while we're waiting for more people to join the webcast. So what I'm asking here is just really, what's your experience level with GCs? You're new to GCs, have very little experience with them, worked with them a little, but still learning, had some formal training, whether that's with the factory or with your organization, and have got some experience with GCs, or if you're an expert and you're really on the call just to try and prove me wrong. So if you can just quickly answer this poll for me. If you're there with a few different people, then just put in your experience level for most people in the room. And I'm watching the results come in now. You can see there that about a third between new to GCs, worked on them a little, and had some formal training. And then there's a few people that regard themselves as experts. So that's good as well. Hopefully we get some really good questions as we go through the webcast as well. So I'll just leave that poll up for a little bit and wait to see when we stop getting results on the poll. Okay, still seeing some poll results come in. Okay, it looks like everyone's answered the question now. We've got quite a few people that have joined us today. So let's start with the presentation. So just to give you an understanding of the environment that we're in today, we're using the On24 environment. So you'll see the slides and video in the middle there. The Q&A, if you've got any questions, if you type them into the box down below, that would be great, because we will post the questions. We'll have a look at the questions as I'm going through the webcast, and I'll answer them. I'll try to answer them as we go through the webcast, although sometimes I'll just wait on until a little bit later, because maybe that information may be in some slides later on in the presentation. So, but if you've got any questions, just put them into the Q&A interface down the bottom. My bio is up there on the top right-hand corner. My name is Shane Hale. I've been with Emerson now for about 17, 18 years now. Started off as a field technician, worked through and did engineering with some international projects based in Australia and around the Asia-Pacific region. Then I crossed over into the dark side, went into sales for a while, moved to the US. I'm now based in Houston, Texas. and I was the business development manager, product manager, and now I'm the director of product management here in Houston. There's a resource list. Actually, we don't have any resources for this particular webcast, but if we had handouts or other information, that would be there. We don't have any media either. If you want to share this to Twitter or to Facebook or to LinkedIn, then you can use that button down there to tell everyone that this is a great webcast that they're on and they shouldn't miss it. If you want to contact us, you want to have a salesman contact you, then you can press that button there. And also there's some other buttons down there which are all about the Q&A and resources and stuff like that. But this is the main details of the environment that we're in today. So let's get on with the actual webcast, the content part. Today we're going to be talking about maximizing GC performance, and we'll really be looking at chromatograms in detail, looking at the heart of the analysis. And so first of all, we'll talk about baseline conditions. How do you know if you've got a good GC or if you've got a good analysis? So we'll look at the baseline conditions. Then we'll look at analyzing the final calibration report, looking at things called response factors and stuff like that. Then we'll look at analyzing and optimizing the chromatograms. That's the detector signal and how the detector signal is processed by the GC. Then we'll look at the diagnostic file, and then we'll have question time at the end. So now, just looking at the poll results from the poll that we had at the beginning. So it looks like the audience is very evenly split between people who are new to GCs and people who are experts. So that's got to be one of the most even splits that I've ever had for a poll in my webcast. So I guess I'll try and cover everything from absolutely new information to stuff that the experts on the call will find useful. That's a very interesting split there, actually. Okay, so let's get into it. So let's talk about baseline conditions. Essentially, one of the things that we're doing here is we're looking at the operation of the GC, the accuracy of the GC, trying to optimize it. Well, the GC will be the most optimized when it leaves the factory. When our GCs and the Emerson GCs leave the factory, we do a whole lot of testing in the lab. We will optimize the timing and the analysis to make it as good as we can. For most of the GCs that leave this factory, we actually have them go through an environmental chamber where we chill them down to 0 degrees Fahrenheit and up to 140 degrees Fahrenheit over a 24-hour period. So, you know, we really stress the GC out, trying to optimize the performance as much as possible. So when we're trying to maximize the performance of a GC in the field, it's really good to understand and know what the GC was like when it was performing at its best. And typically, it's performing at its best when it ships out of the factory. Now, sometimes there may be some changes that are made in the field. Something may not be exactly the way that we were told, and so there needs to be some changes done in the field. So maybe we'll actually use the information from the site acceptance testing. So when the GC goes to site, if there was changes made because maybe there was extra components or a different composition than what was planned for, maybe you'll use that site acceptance testing data, so the chromatograms and the final calibration report from when it was set up on site for the first time. Or maybe this GC's been there for many, many years. It might be 20 years old. The performance would have changed since it left the factory, or maybe that information isn't available. So maybe you'll use the information from the last time someone really overhauled the GC and worked on it and got it up and running and tuned it the last time. But really, when you're looking at maximizing the performance of a GC, you really want to have some baseline conditions to know what it was like when it left the factory, or when it was accepted on site, or when it was last worked on and tuned, and the performance was known to be good. So it's important to have that information on hand when you're trying to maximize the performance of a GC. And what we should use for reference is the configuration is always useful, but really the final calibration report, which we'll be talking about in a minute, and then the final calibration chromatogram from that reference point is the most valuable information, and the information that we're going to talk about in detail today. So the next major section, we're going to look at analyzing the final calibration report to see how well the GC is tuned at the moment. So looking at a final calibration report, we have a final calibration report there on the right-hand side. The final calibration report includes a lot of information, but the most valuable information that we find for knowing if the GC is tuned and performing at its best is the response factors. And the response factors are the response of the detector to each individual component. So unlike a pressure transmitter, which only has really one calibration factor, or some other analyzers that only have one calibration factor because it's only looking for one variable, a GC is relatively unique in that it has a response factor for each individual component, or a calibration factor for each individual component. And you can see there, in this particular application, I've picked a C6 Plus GC because we use them all the time, but it could be any kind of analyzer, any kind of GC analysis. But each component that we measure has its own response factor. And on the final calibration report, we have the new response factors, which is the latest response factors, and the old response factors, and we have what we call here the RF percentage deviation, the response factor deviation. That's the change in the response factor from the latest calibration run and the previous calibration run. And that's useful information as well to know how it's changing over time. But what we're going to do in this presentation is really not just look at the response factor deviation, which is immediately on the report and you can see it there, but also have a look at how to analyze these response factors in a little bit more detail. The response factors themselves can vary due to many factors. The amount of sample that we inject is one of the biggest effects of the response factor, of variance in the response factor. And even though we try to inject the same amount of sample every single time, that amount of injection, the amount of sample that we inject, will change depending on some other factors. And some of these factors include the atmospheric pressure. We inject the sample typically at atmospheric pressure. Now, atmospheric pressure is not constant. It changes with barometric pressure. If you have a low pressure system move in, then the atmospheric pressure will drop, and so the amount of sample that we inject actually decreases, and we'll see that with the response factors. So if yesterday you had a high pressure system, today a low pressure system comes in, the atmospheric pressure drops, the amount of sample that is injected will drop, and the response factors will actually drop. But the thing is that happens for all of the components, so all of the response factors will drop because the amount of sample that's injected will drop. Also, that can be affected by abnormal sample pressure. So say the pressure takeoff is blocked, so the sample pressure drops. If it drops by a dramatic amount, we may not actually fill that sample loop completely, and so you'll see a dramatic drop in the amount of sample that's injected, and so you'll see a dramatic drop in the response factors. Now, the atmospheric pressure changes is okay, we expect that. But if the sample pressure is dropped so that we're not filling that sample loop with sample, then that is a problem. And so if you see big response factor deviations for all of the components, then that's a big problem, and you know you've got an issue with your sample size. The other thing that can affect the response factors is the degradation of detector performance. Over time, the detector performance, whether it's a TCD detector, a thermal conductivity detector, an FID, which is a flame ionization detector, or a FPD, a flame photometric detector, over time, the performance of that detector can degrade. And so you'll see a change in the response factors with a changing of the detector performance. Now, that can include like the coating of the detector for a TCD or even an FID or an FPD. Maybe some contamination gets into the detector and starts coating some of the detector. That will cause a degradation in performance. But the thing with these kinds of changes in detector performance is it will change all of the response factors because it's common with all of the components. So tracking the response factors of the detector, tracking the response of the detector with the components will help identify if you do have measurement issues. And what we often do is we will take those response factors and we will actually chart them. We'll put them onto into an Excel spreadsheet and we'll chart them and have a look at the response factors. Now, looking at the response factors today is useful on a chart because you can tell some issues, but really the value comes when you chart it against your reference conditions. So you chart it against when you know the GC was good. And here we've done that. Our reference is in blue. The latest response factors is in green. You can see that the response factors have changed, but you can see that their variation is consistent. They've all changed the same way. They've all decreased a little bit. This may be because of detector degradation. It may be because of atmospheric pressure change. You know, maybe the reference was when there was a high pressure system, and today there was a big low pressure system come through. Maybe a hurricane's come through the Gulf. We've got a low pressure system come through, and now we've seen a drop in the response factors, but all of the response factors have dropped by roughly the same amount, which means that there's no problem with performance. It just means that the amount of sample we're looking at has changed. So it will still be accurate. It doesn't mean that there's a problem because it's no longer exactly the same as the reference. It just means that there has been a change, but they're all consistent, so everything's okay. If I have a look at the next one, here we can see that our reference is in the blue, the latest is in the green, and you can see here that nitrogen is significantly different than the other response factors. So that tells me that there is a problem with the nitrogen, and actually there's a problem with the ethane as well, which tells me there's something wrong with the measurement. And it tells me that there's something wrong with nitrogen and ethane in this case. So on the left-hand side, we've got a change in the response factors, but because the change in the response factors is consistent for all of the components, then there's not necessarily going to be a problem with the measurement. But on the right-hand side, you can see that the response factors have changed and the change is not consistent across the individual components. It tells us that there's a measurement issue with two components, which is in this case nitrogen and ethane. So the inconsistent change in the response indicates that there is a measurement issue. Now, another way to look at these response factors is to do what we call control charts, where we plot the response factors over time. And here I've only plotted it for a couple of days for each of the individual components. But what we're doing is we're saying, okay, we expect to see some variation in the response factors, but if the response factors vary by too much outside of our control limits, then we want to go and have a look at the GC because maybe something is happening with our sample size. In this case here, you can see that all of the response factors have all started to go outside of our limits towards the end here. Maybe we're getting too much back pressure. Maybe there's something wrong with the vent, and because our back pressure is increasing, it means that our sample size is increasing, so our response factors are increasing, so there's something wrong here. So using control charts where you plot the response factor over time and using that knowledge of that statistical variation that you see in response factors, you can set some alarm limits and say, hey, something is wrong here. Now in this case you can see that all of the components are all doing pretty much the same thing. They've all started going over outside of the control limits with one exception. You'll see there that propane hasn't gone outside its control limits. And so if you were just looking at this, you would say, hey, I've got a problem with everything except for propane. Well, actually that's not true. Everything is changing except for propane, so it actually suggests to me that there is something wrong with propane as well, because everything has gone outside of the limits except for one component, which kind of tells me that something's going on with that one component. So if we track the response factors and look at them compared to the reference condition, which we have down here in blue and the green, I can see that everything has changed except for one component, and it's propane. I happen to know that propane can be affected by valve timing, so it tells me that something is wrong with propane. So one of the main points I want to make here is that if I go back here, control charts are great because they show you what's happening with all of the components, but also we want to look at the component response factors relative to the other components. And that's an important thing to get a handle on, is relative to. And something that we've started doing here at Emerson is we're now using what we call relative response factors, because it's useful to see the change in all of the response factors, but we know that with sample size, atmospheric pressure, and other variations in detector performance will affect all of the components, but they should affect all of the components together. So we worked out that, hey, let's look at this relatively. Let's look at the response factors of all the components relative to a single reference component. And here, in this case here, we've got a relative response factor to methane. So what we've done is we've looked at all the response factors. How big are they compared to the response factor of methane? Looking at the formula there, you have relative response factor equals the response factor of the component over the response factor of methane. So if you look at the chart here, you can see, okay, methane starts off with a response factor of 1 because it's going to be response factor of methane over response factor of methane equals 1. But then I look at the other components, and the response factor of nitrogen is about 1.3. And the relative response factor of carbon dioxide is nearly 1.5. So now I've got a way of seeing what instead of looking at this chart on the left where, okay, I've got a change in response factors, all of my response factors have changed, but have I got a measurement issue of one component? It's kind of hard to tell. Now when we use this relative response factor, we can see if the component, each individual component measurement has changed over time with reference to a baseline component, which in this case is methane. Now, if you don't have methane in the measurement, you can set the baseline component to be anything you want. You can choose any of the components that have been measured as being that reference component. And when you do make that decision of I'm going to compare every component to a particular reference component, a single component, you want to choose a component that's not going to be affected by valve timing, is not going to be affected by other measurement issues, and usually you'll pick the component that tends to be the largest component in your mixture. Now, we've been doing this for a while using Excel spreadsheets, but just to plug one of our products here, in the 370XA, where we're doing a C6 Plus analysis all the time, we actually have incorporated this into the GC. Because we're so familiar with this measurement, we've been doing it many years, now we've set it up to configure this into the GC so that we can really tell if something's going on with the measurement. So what we have here in this table, you see the components on the left-hand side, then the ideal response factor ratio. And this is the ideal response factor to, in this case, methane. So you see there that methane has a response factor ratio of 1, and then nitrogen is about 1.258 larger than methane. And then the response factor of carbon dioxide is 1.509 times larger than methane. And we've set that up, and because we know this measurement, we know the performance of the TCD quite well, we've set up these ideal response factor ratios, and on the right-hand side, you can see that we've set a limit. So that we can set alarms to say, hey, if the component response factor goes outside of this ideal ratio, we know something is wrong. One thing you'll notice here, though, is that we have a reference component table here as well, and some of them are referring to methane and some of them are referring to ibutane. That's because we have two situations in this particular configuration where we have different flow through the analyzer. The flow rate may change through the analytical circuit when we have valve 3 on versus throughout valve 3 off. That happens to be, in this particular application, a dual column valve, so we're switching between two columns. In the ideal world, we would have the flow exactly the same between valve 3 on and valve 3 off, but we don't live in the ideal world, so there are some small variations. And so what we do is we know that when the flow rate changes, it'll change the response of the detector. So the reference we'll use is a component that uses the same flow path as those other components. So with valve 3 on, we use methane as the reference component, and then with valve 3 off, we use ibutane as the reference component, because ibutane in this particular configuration happens to be a component that won't be affected by valve time and usually has a reasonable amount of concentration. It's usually about a % level in your calibration gas, and so we use that as the reference component. And so what we've done with the 370 is we've taken this understanding that the response factors should be consistent over time. They will change over time, but they should be consistent and have a consistent ratio to each other over time. And we're now using that as a further diagnostic to maximize the performance of the GC to make sure that it's measuring as good as it possibly can be. So that's looking at the final calibration report. I'm just looking for any questions. I don't have any questions at the moment. So before I move on to the next section, I might just wait for a minute or two, or for 30 seconds or so, to see if there's any questions about the response factors and the relative response factor, using a relative response factor and tracking response factors to see and to understand if your GC is performing the way it did at that reference condition, which was back when it was either left the factory or accepted on site, or the last time it was overhauled and tuned. Okay, I don't see any questions coming through, so we'll move on. So now we're going to talk about, whoops, I think I have my slides out of order here. We're going to be analyzing and optimizing chromatograms. Chromatograms are the heart of the measurement of the GC. This is the source of all measurement. This is the detector output. You'll see the detector output there in the trace, and from that, the electronics inside the GC will measure the different peak sizes, look at the areas, look at the heights, and calculate what the concentrations are for each individual component. So the chromatogram really is the heart of the source information of the measurement. And so when you look at the chromatogram, this is how you really can determine if you've got the optimized performance, the maximizing the performance of the GC by looking at the chromatogram. So let's have a quick overview for those that are relatively new to GCs, just to get everyone on the same page. Let's have a quick look at some basics of the chromatograms. So for each component that is measured, we have this peak. You can see there the blue trace. You can see a peak there. You can see a little number at the top there. That's the retention time. That's how long has it taken for the for that component to go through the analytical flow path and over the detector. And so each individual component that is measured is represented by a peak. Now, you could have a multiple detector GC where you'll actually see 2 or 3 or 4 traces on the chromatogram, usually in different colors, and each of those traces will be the detector output, and for each peak that you see, that will be a component that's being measured. You can tell what the component is by the retention time. You'll see here, it's a little hard to see on my screen, but you can see there at the top of this peak is 44.8 seconds, and if I look at the table on the right hand side and look up 44.6 seconds, that is going to be propane. So that's how we identify the components as well, is by the time it's taken to go through the analytical flow path and over the detector, which is the retention time. The GC will generally detect the start and the end of the peak automatically. And you can see here, this is you can see this with the little lines above the baseline there. You can see the peak start and the peak end, and anything in between is going to be integrated as a part of the peak. On the Emerson GCs, this is indicated by integration start and stops are indicated by little lines above the baseline. So you can see this peak here, we've got a long line above the baseline, which is the peak start. Then we have a small line here, this is the peak end, and anything in between will be integrated as a part of that peak. And so there's another 2 there. The large one is the peak start, the small one is the peak end. Here we have 2 peaks that are actually very close together. So we have a peak start, and we have here a peak end and a peak start at the same time. And it will actually integrate the left-hand peak from the peak start to the peak end, and then the right-hand peak, it will start the integration from that point as well, and there we have the peak end as well, and actually is technically a start to another 3rd peak as well. So what we can see here is the individual peak ends, the integration stop times for each of the peaks that's being detected on this chromatogram. Oh, looks like my PowerPoint hasn't really come through on this way. The area under the peak is proportional to the concentration of that component. And I've got a bit of a problem here with my slide, and I apologize for that, but the area under the peak is proportional to the concentration of the component. So what this formula should be, if it was written there correctly, would be concentration equals the peak area over the calibration concentration. So, sorry, the response factor. So that's how we calculate what the concentration is, by looking at the concentration of the area that's measured between the integration start and stop over the response factor. Now we can also do it by height as well. And so in that case we would have, instead of area, we have the measured concentration equals the peak height divided by the response factor. Now, note, we don't generally use the peak height for most measurements. We really only use peak height if it's a very long and flat peak, where we may have trouble seeing the exact start and the exact end of the peak, but that is an option to use peak height. Now, we also have some other lines on this chromatogram, and you'll see that there's lines below the baseline. And these indicate timed events, such as valve switching or integration settings, such as peak width or detector gain or something like that. And they are what we call timed events. And if I look at the big chromatogram viewer, what we have here is we have the chromatogram in the center, and on the right-hand side, on the top box here, the top table, is our timed events. And that's all of the individual timed events, such as switching a valve, turning the detection on or off, changing the integration sensitivities. You can see there we've got slope sensitivity and peak width. They are what we call timed events, and they will happen at the same time during the analysis every cycle. Optimizing or maximizing the performance of the GC really depends on getting these timed events set up correctly, because this is going to determine when the valves switch and also when the detection of peaks will start and stop. Now, what we use at Emerson for our detection starting and stopping is what we call inhibits. Basically, we will stop the GC or inhibit the GC from integrating peaks when we aren't interested in looking at what the detector is doing. Say, for in this case here, we've got a valve timing, and we've switched a valve, in this case valve 2, it's called our back flush valve. When you're doing a back flush valve timing, you're actually reversing the flow of the carrier gas and the components through a column, and so you see a very big change in the flow rate. You see some pressure disturbances inside there. We're not interested in looking at those pressure disturbances because we know we're going to get this noise from the valve switch. And so what we do is we inhibit the GC from looking at the peaks when we expect to see this noise. So what we see here is we before we switch the valve, we turn the inhibit on. Then we switch the valve. We've got valve 2 off. This valve noise, this change in the detector output that we see is the valve noise. We're not interested in seeing it, so we've inhibited it. But after that valve noise and before the peaks that we're interested in looking at, we turn the inhibit off, and now we start to look for peaks. So we'll do an inhibit before a valve switch. And also if we're going to change the integration settings. And so here we've got a very large peak. In this case it happens to be methane. And we've got a small peak which happens to be CO2 in this case. And so what we're going to do is we're going to change the gain, because methane is like 95% of the gas and the CO2 is only going to be 1%. So we want to change the way we look at that peak. So in this case here, we've got an inhibit on, so we stop looking for peaks. Then we have a gain change. We have a peak width change, which is a way that we integrate the peak as well. And then once we've changed those integration settings, we'll turn the inhibit off and start looking for peaks again. The important thing with this is when we're looking at the chromatogram, maximizing the GC performance involves looking at these chromatograms and looking at these peaks to make sure that they're being measured correctly, making sure that they're not being affected by these timed events. And also we need to consider what's going to happen in the future. We need to consider what's going to happen, you know, a week away or 2 weeks or a month or 3 months later when we're not at the GC, because these are online GCs. These are running 24 hours a day, 7 days a week without our looking at the GC, without us looking at it. And so we want to be able to optimize what we're doing for the future as well. So let's have a look at what we do here. Well, let's have a look at what can be a problem. Here we have a problem where the inhibit on the left-hand side is too late. And you can see here, what I look for is a line above and below. A line below is a timed event. In this case, it's an inhibit. And a line above is where we've started to see the beginning of the peak. But you can see here that it's pretty clear that we haven't seen the beginning of the peak because the inhibit was too late. The inhibit should have been much earlier. And unfortunately, it's too late, so the beginning of that peak is not detected, and we're going to miss out on the measurement of some of that peak. So the measurement accuracy will be compromised because we're not looking at all of the peak. And this is one of the things that when you're trying to maximize the performance of your GC, this is one of the things to look for. You look to see that the beginning of the peak is easily detected. It's not being forced. In this case here, the inhibit is too late, so we're forcing the GC to ignore the beginning of that peak. And also, if we look at the second half here, the right-hand peak, the inhibit is too early. And so what we've seen is that you can see here that the line is, it's not flat. We haven't seen the end of the peak, so we're going to miss out on all of this measurement because the inhibit, we've told the GC, hey, stop looking for peaks. And so the inhibit is too early. We're going to cut off some of this analysis, and so we're not going to get a accurate measurement. And so this is one of the things that we're going to look for when we optimize the GC, is we want to see that the beginning of the peak is detected correctly and the ends of the peak are detected correctly. The other thing that we need to consider when we're optimizing the GC is that over time, the retention times will shift because you'll get some build-up in the restriction of the valves, which will make the components actually come out a little bit later. And also you've got to understand as well that one of the things with chromatography is that when the concentration increases, the peak actually comes out a little bit earlier. And so what we need to do is we need to set the timed events so that they're not right next to where the the peak will be detected, that there's a little bit of room for changes in the performance. So if I look at here, we've got some peaks on the left-hand side, some peaks on the right-hand side, and in between these peaks, we're going to be doing some inhibits and timed events changes. We don't want to set that inhibit and timed events to be right after those peaks. We want to put them pretty much in the middle so that we give the chromatogram, we give the peak some room to move from left to right so that it will be, it'll still measure accurately even though the retention times may shift. And actually retention times can also shift due to atmospheric pressure changes as well. And so if the peaks shift a little bit, we want to make sure that we optimize the timed events so that we give a little bit of space for the peaks to move so that we're not going to affect our measurement. So that's pretty much how we're going to cover optimizing the GC. But I do have one question. I want to get to this question. Is the reference gas predetermined by the GC configuration? So what we're talking about here is going back to, let me try and go back to where we're talking about reference. Actually, it's the reference component will be determined by the configuration, because every configuration is a little bit different. So if I go back to this slide, I'm just going to go back to the 370 slide. I know I've jumped back quite a bit now, but I do want to answer this question. In this particular GC, we're using it's a C6 plus mixture, relatively complex, but what we're doing is we're using methane as a reference. Now, if I wasn't measuring for methane, maybe I'm just looking at my tower performance and I'm splitting between, maybe it's a de-ethanizer, and I'm splitting between ethane and propane. And I really want to look at just the ethane, propane, and maybe the butanes. So I may not have all of those components, and my majority component may be the ethane. And so in that case there, in that application, the reference component I would use would be ethane. Now, when we set this up as far as ideal response factor ratios in the factory, we'll choose a component that makes sense. It's a large component that won't be affected by valve timing. And that's the two rules there, is a reference component needs to be a large component, that a large concentration component that is not affected by valve timing or other measurement issues. So you know that the measurement's going to be pretty consistent in most situations. So in the factory for a C6 Plus, we're using methane because it's not affected by valve timing, and it's also not, it's a large component, so it's a large concentration component. But for custom applications, for other applications, you will pick a component that will have a large concentration, is not affected by valve timing, but you'll make that decision, because when we're looking at these charts here, these are charts that are not actually configured in the GC. This is something that you'll do with an Excel spreadsheet, and you'll do with your own particular configuration. We are looking at moving these into more of our customized GCs. That's a product development that's happening into the future. But what I'm showing you here is how to look at your GCs that may have completely different components, and also looking at GCs that are out there already. If your GC is out there already, you're not going to have a lot of this software bells and whistles, so you may want to set up these kinds of checks yourself. And this is something that you can do in Excel quite easily. So hopefully that's answered the question. I'll just mark as answered. So let's go back to where we were before. Now, one of the things I talked about is always going back to your reference conditions and always having a look at your reference conditions. And your reference conditions are when the GC was working well, when the GC was working perfectly. And so when you know that the response factors were all in the correct ratios, the response factors were all set up correctly, and it was optimized. So a good thing to do is to save this data for future reference. And this is also a good thing to do to understand that, keep a record that, hey, I optimized the GC, this is how I left it. Things that you should save when you want to set up a reference file or a file to say that everything is okay, a log to say that this is how I left the GC. Things you want to include is the final calibration report, the final calibration chromatogram, the stream chromatograms, and also save the configuration file as well. Another thing that's useful to save is actually the event log, which is a record of all of the changes that have been made, so that you can say, hey, these are the changes that I made. So that's good information to save once you've worked on the GC. We understand that this is good information to save for the GC, and so what we've done at the factory, we've actually put this into our software. And I just wanted to show this off while we're talking about this, is that we have in our Mon 2020 software what we call the diagnostic data function. And what this does is it will save a diagnostic file. And this is good not only for what we're doing here, which is optimizing the GC, but also if anyone has problems with the GC and they need to send you information, or you need to send information to the factory or to one of our service technicians, rather than saving a calibration chromatogram separately and saving a final calibration report separately. We've developed this little tool that allows you to save the diagnostic information all as a single file. So what you need to do is go to Mon 2020. This works with all of the XA GCs, the 700XA, the 370XA, and the 1500XA. So you go to Tools, Save Diagnostic Data, and then it will save a file. Create a file with analyzer name and date. And one of the really cool things is it will actually prompt you to email the file, and it will automatically attach it to a email so that you can send that file to anyone. It's only like a 450 kilobyte file. And then once you've set that file, you can then view that diagnostic data. And to view that data, you just go to Tools, View Diagnostic Data, and this is where you get to see, you choose the file, and this is where you get to see all the information that's in there. It actually opens up as an offline configuration, and then it includes all of this information. So it has a stream chromatograms for each individual stream. It has the final calibration chromatogram. It has the final calibration report. If you've got validations configured in there, it'll save the validation reports and chromatograms as well. Any protected chromatograms, which may be the factory chromatograms or site acceptance testing chromatograms, they are saved as well. And also we have this Modbus trace, which is a communications log for the GC as well. And also inside this diagnostic file is the alarm log and what I like to call the lie detector, which is the event log, all of the changes that have been made in the GC, and also all of the configuration information, which includes the component data table, the timed events table, the Modbus maps. All of that information is all saved in that one little diagnostic file. And so I wanted to show you this file because this is a great way of saving a reference file, so that if you're going to optimize the GC sometime in the future, you can have this reference data all saved together as a single file. And also if you do have problems and you want to send information off to an expert, whether it's a service engineer for Emerson or your own experts, this is a single file that contains all the information that they could need to help you diagnose any issues. Now this does require the most recent version of Mon 2020. It needs to be version 3.1.4 or higher. It does not require any updates to the GC. So if you've got a 700XA, a 370XA, or a 1500XA, it works on those GCs already. You don't need to download any firmware. You don't need to do anything with the GCs out in the field. It's just the software that's on your computer, which is the Mon 2020, and you can get that software on our website. It's available free on our public website. There's the page here. Actually, if you go to Google and you go Mon 2020 software, it'll take you almost straight away to this page, and you can download the software for free. We don't sell our software. We understand the only reason you're going to use our software is to use our GCs, and so we give you the software and we'll give you the latest versions here on the public website. So if you do have XA series GCs, I highly recommend that you get everyone in your system to upgrade to the latest version of Mon 2020 because of this diagnostic file. It's a really useful way to be able to save and share diagnostic information, and also an audit trail of the information that's inside your GC and the configuration of your GC. So we've got about 7 minutes to go now, so this is a good time for us to start to finish up, and a time for you to ask any questions. So if you've got any questions, please enter them into the Q&A box down the bottom, and we'll try and answer your question. So I'm waiting for questions to come through. Don't be shy. I know we went quite fast through the presentation today. There's a lot of information in there. Hopefully it gives you a good understanding. Okay, I've got a question here. Is this data available in the MON 2000? All the individual data is available, but the actual diagnostic data file is not available in MON 2000. It's only for the MON 2020 software, and that's simply because MON 2000. To give you an understanding of why we have MON 2000 and MON 2020, MON 2000 is for our legacy GCs, our Model 500, Model 1000, Model 700 GCs. That software actually started as DOS software, MS-DOS software. So it has a very old code base. It has a very old way of doing coding. And a lot of the functionality that we need today in modern Windows programming environment is just not available in that MON 2000 DOS base code base. And so we've had to make a decision to develop on MON 2020, and unfortunately MON 2000 is pretty stable now. Well, it's very stable, and we're really not adding new features to MON 2000. So unfortunately, the diagnostic data function is not available in MON 2000, but it is available in MON 2020, which is used with all of the current generation, new generation GCs, the XA series. But saying that, the chromatogram, the final calibration report, the audit log, the event log, that can all be gathered manually and sent over email as well. Okay, waiting to see some questions come in. We always get the questions about, will the presentation be available at a later date? The presentation is available on, this whole webcast will be available as a recording. It'll be available within the next 24 hours, and you should get an email by the end of the week with a link to the recording that you'll be able to forward to anyone in your organization and use again. The actual PowerPoint files, we don't generally give out our PowerPoint files, and we would only give out a PDF personally. So, but the recording will be available. It'll be available for the next couple of years. Usually these kinds of webcasts stay alive for 2 or 3 years, and so that's not a problem. Okay, I've got a question here to go and cover the Inhibit on-off again. Let me go through here. Well, let me find it. Okay, here we go. Okay, so just a quick review of how the inhibits work. Essentially, the inhibit is inhibiting the GC from looking for peaks. And you can see these timed events. Timed events are always lines below the baseline. So this blue detector trace, lines above will be integration, peak starts and ends, but the lines below are the timed events. And you can tell what the timed events are by looking at, you can see that on the chromatogram here, you can see all of these lines below the chromatogram, the baseline, and they are timed events in this table. And you'll see on the right-hand side of the table is a list of times, and so you can match the timed event below here with the time that's on there. And actually, when you look at a chromatogram, I don't have it shown in this particular presentation, but you'll see there that one of the timed events is actually red, that means it will be highlighted in the timed events table. On this particular chromatogram that I'm looking at now, the timed event, unfortunately the timed event that's highlighted is the first one, so you can't see that it's red because it's right at the edge of the chromatogram. But if you move this crosshairs across the baseline, the closest timed event will be highlighted in red, and that'll be highlighted in the timed events table. And the way the inhibits work is that they will stop, so you'll see a line below the chromatogram here, which indicates, there we go, indicates an inhibit on. You'll see in the table that at about 19 seconds you'll see an inhibit on. Then you'll see this valve 2 is another line below the chromatogram, below the baseline. That's valve 2 off, and then the inhibit off. And this one here, if I was to look at the timed events table, because this one is red, you would see that would be highlighted in the timed events table, and that's an inhibit off. And so now you can see that we turned the inhibit on here. Anything between the inhibit on at 19 seconds and the inhibit off at 28 seconds will be completely ignored by the GC electronics as far as detecting peaks on or off. Hopefully that's helped you there with the review. Once again, I'd like to say that you can always go back and look at the recording again and review the entire presentation. I'm just looking at the questions here. Okay, it looks like questions have slowed down, or actually stopped. So, so we'll draw it to a close. I'd like to thank everyone. Thanks for your time. Before you go, though, we do have a poll at the end. I want to know how useful you thought this was. But thank you for your time. We do have another webinar planned in October 20, sample handling considerations of your gas chromatograph. We did run into a bit of a scheduling problem. We found that one of our competitors decided to start, when they found out about our schedule of webcasts, they decided to schedule one of their webcasts in the same week. Apart from being very rude, our people have said, well, why don't we give you less time to schedule? But my personal opinion is I want to give you lots of time to know when these webinars are going to be, so you can organize a big group of people to watch them. So our next one is going to be October 20. We'll see if our competitor decides to plan a webcast at the same week as that. Maybe you can write in and vent your frustration at them. But October 20, sample handling system considerations for your gas chromatograph. Also, all of the other webinars that we've done before are all available on our website. The easiest way to find it is to just go into Google or to your search engine of choice and type in Rosemount GC webinar, and that will take you directly to the page. Or if you really want, you can click on the hyperlink there. That'll take you directly to the webinar series as well. If you've got any other further questions or comments, you can contact us at the analyzers@emerson.com email address, and we will answer you. So now I just want to put up a poll just to see how useful you thought this was. Did you think it was awesome, very good, good, not helpful, or a waste of your time and you'll never get that hour back? So it really helps us if you answer these, so we can make sure that we are you know, really giving you what you want. So if you can answer this poll, that would be great. And that's it for me. I'd like to say thank you very much for your time. I know everyone is busy out there, but I really appreciate your time, and I really appreciate the effort that you've made. And once again, the webinars are going to be available as a recording, so you can go and review them yourself over time, or you can send them and forward them on to any of the people that you work with, so that they can use this information as well. So once again, thank you very much for your time, and that's it for me. See you on October 20. Thank you very much. Bye-bye.